Hello, everybody. My name is Douglas Guilbeault. I'm an assistant professor in the Management of Organizations group at the Berkeley Haas School of Business. I'm really excited to present this work to you today with my advisor from my PhD, Damon Santolo, who's at the University of Pennsylvania. And essentially what we've done is develop a set of network measures for identifying and predicting the spread of complex contagions through social networks. Complex contagions are social behaviors, innovations, political beliefs that require peer reinforcement as they spread through social networks. Now, because this work is currently under review, I'm not going to go into great detail on the mathematics side just to make sure that the review process is smooth. What I will do is give you an overarching picture about what the theory of complex contagions means for our theories of influence and centrality in social networks, and I'll discuss some of the simulated and empirical results we have that explore a model of social influence based on complex contagion. So there's a popular myth regarding how behavior spreads that was perhaps most epitomized in the work of Malcolm Gladwell, which is captured in this quote here. I'm convinced that ideas and behavior spread like viruses. This isn't just a metaphor. In other words, I'm talking about a very literal analogy. Ideas can be contagious in exactly the same way that a virus is. So this notion of a strictly empirical analogy between viruses and then social phenomena like ideas, behaviors, technologies, to say that they're one and the same has led to a number of assumptions regarding how network structure is expected to mediate the spread of social behaviors and innovations. One of these intuitions is perhaps most famously codified in the small world network model, the original studies surrounding that. This was the idea if you take a regular network with consistent tie structure, a k regular, degree regular network, and you randomize some of those ties, so you keep the number of connections constant, but now you've created long ties that stretch across the network, that essentially you will accelerate the spread of a contagion. Now, this has direct relevance, of course, to the spread of biological pathogens and relates directly to why people are concerned with international traveling and flights. One person with a particular disease, as we know during a pandemic, one person coming on a plane to a different country can trigger the spread of that disease, and that would be a long tie across the networks. And random networks where this connectivity is distributed is expected to have the greatest effect on accelerating the spread of these contagions. Now, underlying this notion of spreading, in which applies in that case particularly well to biological pathogens, is this measure of shortest path length, which is one of the most foundational measures of network structure and social distance. It's basically the smallest number of single ties or edges in the network that a contagion must traverse when spreading from one node to another. The key thing to notice here is that the notion of path length has often been actually conflated and defined as one of the same thing as defining the distance that a contagion must spread in the network. And this can be readily seen by Milgram's famous 6 degrees of separation experiment, which had the following design. Basically took a particular source in the network and said, I want you to send a package, like a mail package, to another person somewhere else in the country in a peer-to-peer fashion. So you have to send it to someone else who then sends it to someone else, and then wanted to track how many steps in the network it took to get the package from one person to the other. We can say we started Rajat here and say Arnold is the target. Basically, the finding was that as you track the path of peer-to-peer spread of this package, you tend to see that people are within 6 degrees of separation, where the degrees here refers to 6 ties throughout the network. So here, the notion of a path is directly instantiating a notion of distance regarding the spread of a particular contagion. Now, the problem is that this model assumes that a path of single ties is sufficient for spreading a contagion. But that really only works well for the biological pathogen model where exposure to one other person is actually sufficient for adopting the contagion. This is literally someone coughing on you in the age of COVID or sneezing on you for the flu season. But that only really captures a small subset of the things that spread through society. Actually, we refer to the biological pathogen model of contagion as simple contagions. And one analog of a simple contagion in human society is something like factual information, such as the information of who won the election or who won the Super Bowl. You only really need to hear it once from one person to get the information. However, A myriad of contagions in society actually spread as what we call complex contagions. And these are things that spread by exposure to multiple people. You require peer reinforcement. You can think of friends, seeing one person wear some novel piece of clothing isn't enough to trigger adoption if someone needs to think that a given article of clothing or fashion has to be sufficiently popular before they're interested in adopting it, because only then does it actually have some social cachet or social value to them. You have health behaviors like exercise. If you're running down the street and you see someone exercising, jogging, you don't instantly get infected with jogging and start running your the rest of the way home. Instead, some of these behaviors are rather costly and require a lot of repeated peer reinforcement to actually influence someone to adopt. And so here we have this idea that single ties are not enough to enable the spread of the contagions. In fact, we need peer reinforcement or clustering, or as I'll get to later in this talk, we need sufficiently wide bridges. For those of you unfamiliar with complex contagions, first I want to talk about in general how to spot complex contagions. And you'll see that once we look at the mechanisms underlying complex contagion, uh, this actually revealed how the vast majority of contagions in society actually spread like complex contagions. And I'm indebted to my advisor, Damon Santola, for laying out this critical typology of ways that complex contagions can spread in social systems. So first we can think of complementarity. So these are examples where an innovation or behavior actually depends on other people also using that technology behavior for the technology behavior to be valuable in the first place. A trivial but clear example, something like the phone. Having a telephone only works and is only valuable if multiple people have it, so you can call it on them. So it has this interdependency of usage. And social media is of this nature, and for that reason, in fact, various studies like by Uganda et al. And Facebook show that technologies like Facebook spread like complex contagions, technologies like Twitter spread like complex contagions, because it's really only when a critical mass of other people are using it so that actually has that social value. And spoiler alert, things like COVID masks are also a great example of a complex contagion that requires complementarity, because it only really helps reduce the spread of COVID if everybody is using it consistently. Another mechanism is legitimacy. This is cases where the more people who adopt the behavior, the greater the expectations that others will approve of the decision to adopt. And an interesting way to think about this is, for goods that primarily are geared towards social signaling, things like what constitutes a popular fashion trend, or Veblen goods like highly expensive, exorbitantly expensive diamond bejeweled shoes, which gain their value if they're approved by other people, and there's an example that other people are adopting this, and that adoption actually further signals value in pursuing otherwise seemingly arbitrary goods. Another good example is credibility. So these is content, beliefs, arguments that require exposure to multiple different sources to believe in the content. And this has direct relevance to political movements and memes. And a great example comes from a study of the spread of the equality sign on Facebook, which was signaling support for the LGBTQ community. And here it was found that people often required exposure to multiple different peers to adopt, because adopting this signal could be rather costly in their political network. So especially if someone was a broker, which means that they have connections both to say right-wing people and left-wing people, they were to adopt this, even if at the individual level they are fully in support of LGBTQ rights, adopting this could trigger conflict or controversy among different members of their network. And so for fear of that sort of social awkwardness or being avoiding confrontation, they might not, until they see that a sufficient number of people in their network, ideally from both sides of the political spectrum, have adopted this, and now the cost to adopting this are much lower. The likelihood of triggering argument, controversy, and so on are much lower. So this is one of the ways in which complex contagions in the political space can readily emerge. Now, final is a kind of emotional contagion where people are more likely to adopt something the more that they get the fact that more people are adopting it indicates that more people are excited. You get a kind of feedback effect about the potential social value, the emotional payoff of adopting something. And this explains how things like pet rocks can spread, where a big part of it is just thinking that other people think it's cool, even though on its own, it can be arguably verifiably rather absurd. So the question is, are the best network positions for spreading simple contagions the best for spreading complex contagions? That's the basic inquiry that we're exploring in the present paper. We can think of standard measures like degree centrality, other centralities we'll go into, which have looked at the network structures that actually do accelerate the spread of simple contagions. So degree of centrality, of course, is measured by the number of single ties that a given node has in their local neighborhood. And it plays out in this idea that degree centrality here is relying on the notion of a simple path. And by simple path, I mean a single tie that can spread its simple contagion. And this represents this folk theory that people get influenced by being popular. So the people who are popular have more connections that actually allows them to become quote unquote influencers. And the traditional approach of viral marketing for years has been to target these influencers on the notion that degree centrality is the key source of influence in social networks. Another key measure of influence is betweenness centrality. So this essentially argues measures who is necessary for getting information or other content in social networks from one person to another. So it's measured by the number of short and simple paths that pass through a node. So here you can see in the visualization that the node with the highest betweenness centrality is basically in between a separate cluster and the main, larger cluster in the middle. Now the notion here is that these people with the nodes with the high betweenness centrality correspond to this popular notion of a broker, people who broker between communities. And the theory of influence here is really that brokers have this added outsized influence given their ability to control the flow of information between social groups. Now, another source of influence for brokers is the structural whole and good ideas argument, which is that brokers gain access to a wider spread of ideas. They're exposed to different values, cultures, ideas, innovations from separate communities that may otherwise be unaware of what's going on in different communities that they're not connected to because of structural hold. The broker has privileged access to all the sources of innovation and different their cultural variation in their network, and this gives them the capacity to be generative of new ideas that derive from their ability to synthesize what they're exposed to develop a unique perspective. Now, the intuition that we explored and for the rest of the paper was really, well, you can see how something like this traditional theory of brokers doesn't really apply to complex contagions in the sense that the connectivity of the local ties of the broker might not actually be mutually reinforced enough to actually spread a complex contagion if you were to seed contagion from the broker. They might be good at blasting a simple contagion and accelerating its spread to different parts of the network, but if complex contagions require peer reinforcement, the broker might not be a part of communities where the local connectivity among their contexts is strong enough to enable the spread of the complex contagion. And this really challenges our typical notion of the influencer. And what we explore in the paper is really how do you go about characterizing the local connectivity of a node's neighborhood to determine whether or not it's sufficient for spreading a complex contagion. And it turns out this supports a variety of measures that greatly improve our capacity to model and predict complex contagions. Now, the key idea is that if we look at the small world network model with these long ties, we see that they accelerate simple contagions, but they block complex contagions. So here we can see in the spread of a simple contagion with the threshold of adoption equals 1, where threshold means they only need to be exposed to one other person, the simple contagion rapidly darts around the network and reaches global saturation. Now, if we look at a complex contagion, where all we simply do is for each node, we increase the adoption threshold to 2, where now they actually need to be exposed to 2 separate sources of influence to adopt the contagion. This is what the spreading dynamics look on the small world network. And you'll notice that unfortunately, this anticlimactic result that there's no spreading at all. And you can see at the top where we have the initial seeds, the key problem is that the node to the right, to the left of the initial seed actually doesn't share 2 ties with the original seed node. So the complex contagion simply cannot take off and spread in that direction. And similarly, for the other side of the network neighborhood lacks that kind of connectivity. So basically the spread of the complex contagion is blocked. So when it comes to complex contagions, we require dense and relatively equally distributed connections across the network for the complex contagion to successfully spread. And what we do is we go about figuring out how to measure that, what characterizes paths in the context of complex contagion, and what characterizes paths that are sufficient for spreading complex contagion. There's some surprising implications here that we'll get to. So we have this idea that the most influential people for spreading complex contagions are not the most popular people and not brokers. This requires a different way of thinking about node centrality and node influence in social networks. And in fact, it helps make light of what has been described as hitherto paradoxical or anomalous diffusion results, where it's been found that nodes with low degree between centrality are not the most influential nodes in the context of social movement, health behaviors, political news, and so forth. So we provide a theory that makes sense of these puzzling results by saying that this is really because the contagions in these contexts are complex contagions, and the nodes that have the highest influence in the context of complex contagion, we can show are verifiably those that do not have high centrality according to standard measures. So our theory basically starts off by distinguishing between simple versus complex paths. I won't go into great detail into how we measure this, just to say that if you compare the highlighted path by red, we see that there's a chain of bridges of peer reinforcement that enables the conductance of the complex contagion, whereas the blue line exhibits your traditional simple path between the seed node I and the target node Q. And it's just to illustrate visually that what we actually see for the spreading path of simple contagions, they are verifiably different than the spreading path of a complex contagion. So we essentially develop a measure for identifying these complex paths. And to get a sense of what makes up a complex path, they consist of what we call locally sufficient bridges. So we can see the red nodes here and take them as the seeds. So this is where the complex contagion is starting to spread. And if the threshold for adoption is 2 and our target node is that green node there, we can see that they have a sufficient number of connections to the already activated nodes in the seed, and so they can adopt. But if we were to say, look at this node here that is only connected to one of the seed nodes through a single tie, we don't observe adoption because they don't reach the sufficient threshold, and we say that that's because the bridge is not sufficiently wide. Essentially, we develop mathematical techniques for characterizing across all local network configurations whether the connectivity is sufficiently wide or not. And then we can characterize that for all neighborhood connections within a graph and get both local and global measures for the likelihood of complex contagion spreading, where complex paths basically consist of chains of these locally sufficient bridges. And so what we find is the fraction of locally sufficient bridges actually really accurately predicts the likelihood of a global cascade when seeding a complex contagion across a wide range of thresholds. So here we're looking at k-regular graphs permuted over different randomizations of how random the tie distribution is, and this is just playing off the canonical approach to measuring simple path length in the context of simple small world networks. And what we see is they're almost precisely the same in terms of the frequency of one corresponding to the other. This result just illustrates that we generalize this to a wide range of randomized scale-free networks with different levels of clustering using the Holman-Kin algorithm. We see that the average bridge width of a graph is highly predictive of the proportion of adopters. And then exactly as we'd expect, if we track the average complex path length of a graph, we see precisely the same results. And this makes sense because, of course, uh, complex paths consist of chains of sufficiently wide bridges. Now, these measures of complex paths, they support a measure of influence that is complex centrality, which we can identify as nodes with the highest average complex path length throughout the graph. And basically, these are nodes that participate in the longest and most robust chains of wide bridges throughout the network. And so what we then do is we can compare different nodes and neighborhoods in terms of their capacity to seed complex contagions. We simulate diffusion on the AdHealth data set, which is 74 distinct adolescent peer networks. We compare popular centrality measures and their ability to spread complex contagions. What we find is that complex centrality drastically outperforms all existing popular centrality measures for spreading complex contagions in terms of the overall fraction of adopters that you expect to observe. And we illustrate this across a wide range of conditions, very robust to all kinds of different network structures and assumptions about the diffusion process, including assumptions about the diffusion model. We also replicate these results in the context of the linear threshold model and the independent cascade model. Now, crucially, what the other bar plots here are showing is we can look at among those nodes that are identified as most central according to each of these measures, how do they also factor along the other centrality measures? And indeed, we find that the nodes identified with complex centrality actually have putatively low centrality according to the other standard measures, including between the centrality, degree centrality, percolation centrality, eigenvector centrality, and where they fall in the K-shell decomposition of a network, which is just to say, much more quickly, that nodes with high complex centrality occupy the degree periphery of a network, and they actually don't have high influence according to our common notions of popularity, brokerage, and different iterations on that in the context of algorithms, relations, and lastly, and something that I'm most excited about is we can then take these measures to empirical data sets, such as the spread of microfinance and the Banerjee AL science paper, looking at the spread of a microfinance program in 43 distinct rural villages in India. And there's good reason to expect that this microfinance program spread the complex contagion. And indeed, we show that we can outperform all existing popular measures of centrality and our ability to actually predict which households in these rural villages in India were most influential in the spread of this microfinance program. And overall, the complex average complex path length of a village, which is highly predictive of the overall proportion of households in that village that adopt. And one way to think about this is the overall connectivity of households in a village in terms of complex path length is before any contagion is released, gives you a sense of the likelihood of being able to spread any complex contagion on that in that population. In conclusion, we find that complex behaviors very much do not spread like simple viruses, and in fact, thinking about complex contagions requires a new way of thinking about network distance and social influence. We find that traditional influencers and brokers are not the most influential for spreading complex contagion, and in fact, nodes with the highest complex centrality have the low centrality according to these other measures of centrality based on simple path length. And the huge important take-home message here, in addition to these theoretical insights, is that for policy reasons, we're looking to spread new innovations, health behaviors, political messaging. In fact, we have to pay attention to the power of the periphery, which is where nodes with high complex centrality belong. And so actually we need an alternative framework for thinking who's actually going to be the most influential actors when using policy to spread new and important contagions in social systems. So thank you so much. Here is my email, my GitHub, where you can see my code and data for a variety of my projects. And here's my faculty website. I strongly encourage you to reach out to me. And thank you so much for your time.